Good morning all. Welcome to the lecture series on operating system. Subject code is KCS 401. Myself Rekha Baghel, Assistant Professor Ajay Kumar Garg, Engineering College, Ghaziabad. So lecture overview. In this lecture, we will discuss critical section problem. What is the solution of critical section problem? Race condition, and what is the connection between critical section problem and the race condition. How we can solve a critical section problem using the semaphore. Next, we will discuss about different types of semaphores, binary semaphore and counting semaphore. Critical section problem. Critical section is a code segment in complete program where processes access shared resources. Shared resources, what I mean to say, shared resources are like common variable or a file, some input-output devices where all the processes accessing that input-output device. So suppose our code is performing some write operation on some common variable. As multiple processes are executing concurrently, any process can be interrupted in the mid of its execution. Due to partial execution on shared resources by processes, I mean here we can say shared variable can lead to data inconsistencies. This situation is known as a race condition. So we can define race condition leads to inconsistent states of data. Therefore, we need to synchronize protocol that all the processes to cooperate while manipulating on shared resources, which essential is the critical section problem. So race condition is a problem where multiple processes trying to update some common variable or try to perform some write operation on some file while other processes accessing that file simultaneously. So all the entire processes have to wait to run in their critical section. This is the solution of race condition. So before proceeding further, we need to discuss what is race condition and how we can remove this condition with the help of some algorithm. So, for example, consider a bank that stores the account balance of each customer in the same database. Now, suppose you initially have X rupees in your account. Suppose the X rupees are X X rupees are 50 rupees. As you're taking out some money from your account after the transaction, the total balance left will be lower than X. And you just, for example, you take out some amount of money from your bank account, and at the same time, someone tries to look at the amount of money stored in your bank account. So initially in your account you have a 50 rupees. Okay, if P1 process, there are two processes, P1 and P2. So P1 process is trying to read the amount stored in your account, while P2 process try to deposit some amount in your account. Suppose P1 is read on X and P2 try to write. Suppose there are two processes, P1 and P2. P1 process try to read the amount of your balance, amount of your account, and P2 process try to deposit some amount in your account. So P1, when P1 trying to read the amount balance, P2 process try to deposit some amount like 10 rupees to your account. So both the processes are performing simultaneously. So P1 process is unable unaware that someone is also updating the account balance. So when P1 reading the account, the result that it is showing is P1 is equal to 50, while P2 deposit 10 rupees to this account. So P2, for P2 the account balance is showing 60 rupees. So at a time the value of X is 50 and 60. So this is a data inconsistency. So this is the problem of race condition when both the processes are saying that their result is correct. So, but transaction takes some time and hence the person read X as your account balance, which leads to inconsistent data. If in some way we could make sure that only one process occurs at a time, we could ensure consistency of data. If we can just make sure that only one process can access this shared variable, then this race condition problem can be removed. So, if process 1 and process 2 happens at the same time, user 2 will get the wrong account balance as Y because of process 1 being transacted when the balance is X. So, inconsistency of data can occur when various processes shared a common resource in a system which why there is a need for process synchronization in the operating system. So, this is the race condition, and the solution of race condition is to ensure that only one process can access the shared resource at a time. So, we can just remove this inconsistency of data or race condition. So, next example is, if a process 1 is trying to read the data present in a memory location, while another process 2 is trying to change the data present at the same location, there is a high chance that data read by the process will be incorrect. So, similarly, if some variable X stored at some memory location and the value of X is 100, there are three processes: process 1, process 2 and process 3. Process 1 and process 3 are performing the read operation, while process 2 is performing the write operation. Write operation, that means the process 2 is trying to update the value of X. So, when process 1 and process 2, process 2 start first. Process 2 just update the value of 100 by 500. Okay, update the value of X by 500, while process 1 and process 1 and process 3 simultaneously reading the value of X. When process 2 is performing some write operation on X, it takes some time. So, meanwhile, process 1 and process 2 access this value and showing the result 100. Okay, X is equal to 100, while process 2 completes its execution and it updates the value by 500. Now, process 2 showing the value 500. Process 3 also showing the value 100. So, there is a one variable. This X variable is a common variable because all the processes are performing the operation on this same variable. So, this is the data inconsistency. So, this is the next issue that arises due to race condition. How to avoid race condition? To guard against the race condition, we need to ensure that only one process at a time can be manipulating the shared variable counter. that part of program where the shared data is accessed is called the critical section. If we could ensure that only two processes were ever in critical section at the same time, we could avoid the race condition. So we can say critical section is a solution accessing a critical section at a time by only one process is the solution of a race condition. Critical section. What is critical section? Critical section, we can define critical section is a part of a program where that part is shared by the multiple processes. The entry section handles the entry into the critical section and it acquires the resources needed for execution by the processes. So we are saying that critical section is the part of a program where the multiple processes sharing the resources or performing some operation on the shared resources. Shared resources are some file, some common variable or some common input-output device. So, critical section, whenever some process want to enter into the critical section, that process must execute this entry section code first. If the process successfully executed the entry section, then that process is allowed to enter into the critical section. After completing the critical section task or performing the critical section operation, that process must execute the exit section code. So, this is the common solution or this is the common method to allow one process can enter into the critical section at a time. So, if n number of processes are trying to enter into the critical section, then the processes, if n1, n2, then all the processes first execute the entry section code, this code, entry section code. After executing the entry section code, then these processes can enter into the critical section. So, exit section handles the exit from the critical section. It releases the resources and also informs the other processes that the critical section is free. So, we say that critical section is a part of code where some resources are shared. Okay. So, this is the critical section, and what is the solution of this critical section problem? How we can make sure that only one process can enter into the critical section? So, we have mentioned that there is a entry code and some exit code. Whenever a process get into the critical section, that process must execute the entry section code. After executing the critical section, that process must execute the exit section code. So, how we can what is the phenomena that we can apply into the entry section code and the exit section code? So, this is the solution to the critical section problem. We need these primary and secondary conditions for entry section and exit section. So, primary conditions can be formed by two conditions. First one is mutual exclusion and second one is progress. Secondary conditions are bounded waiting and architectural neutrality. So, we will discuss all these conditions in detail one by one. First condition is mutual exclusion. In simple words, what does it mean by mutual exclusion? Mutual exclusion means only one process is allowed to enter into the critical section no other process can enter at the same time. Mutual exclusion. So when a process is executing in a critical section, then no other process can be executing in their critical section. It consists of a single process temporarily excluding all others from using a shared resource in a way that guarantee the integrity of a system. Mutual exclusion, for understanding the mutual exclusion, we can take one example, like when one faculty is in a classroom, then no other faculty can teach the same class at a time. Okay, only one faculty at a time can teach the students in that particular class. So this is the example of critical section. And critical section here, critical section is a class, and mutual exclusion is only one faculty is allowed to teach the student at a time. So it consists of a single process. So in case of, if we are talking about the processes, so when a process is executing in the critical section, then no other process can executing in their critical section. It consists of a single process temporarily excluding all others using a shared resource in a way that guarantee the integrity of the system. It also ensures that when one thread is functioning, read or write functions or operations, then others avoid it to doing the same on the shared data. So all other processes are not allowed to perform some operation on that shared function or shared variable or shared input output devices or shared file. So these are the shared resources. How we can ensure that mutual exclusion is applied to our entry section or critical section? So there are the 4 conditions that can be applied on mutual exclusion. So these 4 conditions are: first condition is mutual exclusion must be guaranteed. Mutual exclusion must be guaranteed between the different processes. When accessing the shared resource, there cannot be 2 processes within their respective critical section at a time. Okay, so this is the first condition. Second condition is no assumptions should be made as to the relative speed of the conflicting processes. Third condition is no process that is outside its critical section should interrupt another for access to the critical section. When more than one process wants to enter into the critical section, it must be granted entry in a finite time. That is, it will never be kept waiting in a loop that has no end. So these are the 4 conditions that must be applied whenever we want to design some solution to the critical section problem. For applying the critical section, for applying the mutual exclusion on the critical section, these 4 conditions must be used. So second primary condition is progress. Progress means if no process is executing in its critical section and some process wish to enter their critical section, then only those processes that are not executing in their remainder section can participate in deciding which will enter its critical section next. And this selection cannot be postponed definitely. Means if critical section, if no process is executing in critical section, then all the processes those are not executing in their remainder section. If process is executing in remainder section, it means that process is already executing its critical section. So all the processes which are not executing in the critical section are allowed to enter into the critical section, but one by one. No more than one process is allowed to enter into the critical section. So bounded waiting, this is the secondary condition. Secondary condition means it is not mandatory but it is desirable to apply. Bounded waiting means after a process makes a request for getting into the critical section, there is a limit for how many other processes can get into the critical section before this process request is granted. So, after the limit is reached, must grant the process permission to get into the critical section. So, purpose of this condition is to make sure that every process gets the chance to actually enter into the critical section so that no process serves forever. If any process, there is a process P1 executing critical section 10 times, P2 process executing critical section 20 times, but P3 process is still trying to enter into the critical section. So, bounded waiting means we have to set some limit on the processes that can enter into the critical section, means this limit. So, we have set some bounded waiting means limit that a process can enter into the critical section, this limit, so that all the processes have a chance to enter into the critical section. This is the bounded waiting. So, we bound the waiting, we bound the limit of waiting into the critical section. Architectural neutrality. Architectural neutrality means when our solution is functioning perfectly on architecture, then it should execute on the other ones also. Hence, our technique must be architectural neutral. So, this is the architectural neutrality. Next, we can move to the semaphore. So, we have just discussed here, like whenever there is a critical section, we must make sure that only one process can enter into the critical section, and we have just designed some entry code and some exit code. So, how we can design a entry code and exit code? We have also discussed the basic conditions for mutual exclusion, how we can apply progress, how we can apply bounded waiting. So, how we can all these together form a solution for the critical section problem. So, semaphore is a integer variable that can be used for mutual exclusion. Okay, so semaphore, we can define semaphore in such a way that semaphore is simply a integer variable that is non-negative and shared between threads. So, it is a integer variable. This is very important. This is a integer variable. A semaphore, or we can say semaphore, is a signaling mechanism, and a thread that is waiting on a semaphore can be signaled by another thread. Means we can say semaphore is basically represented by S. So, S, semaphore can be defined as a signal, can be defined as a signaling mechanism, and this semaphore can used on two atomic operations, wait and signal, for the process synchronization. A semaphore either allow or disallow to the resource depends on the current status of S. So, there are mainly two types of semaphore. The first one is counting semaphore and second one is binary semaphore. So, we will discuss these binary semaphore and counting semaphore in our further lectures. Thank you.